So we are going to go ahead and talk about another section of shear and moment diagrams. So yesterday, um, we noticed that there was what appeared to be a functional relationship between the loading, Wx, the shear diagram, and the moment diagram. And specifically, it looked like there was some sort of derivative relationship between the loading, the shear, and the moment. And there is. And what we're going to do today is we will talk about how we come up with that relationship and formalize it more particularly. We observed it, so now as engineers we need to put it to math. And the way that we're going to do this is we're going to look at the derivative, or not the derivative, rather, sorry, the free body diagram of a small section of the beam. So I'm going to take a chunk here and a chunk here, and we're going to analyze a section of the beam delta x wide. All right, so let's draw the free body diagram of this. So let's blow this up. Here's that chunk of the beam. We've got some chunk of that distributed load, Wx, at the top here. And we have our shear, V, and our other shear, V, here. And let's label this, right? This is delta x wide. That means from some origin here, we've gone x, and then we're going to go delta x more. So that means that the shear is Vx plus delta x. Right, so we've got V at some distance, right? So that makes this one V sub x. Okay, so that's V sub x, so this is Vx plus delta x, and then we have moment, obviously x plus delta x, and then here with our sign convention we just have moment x. All right, and Wx is pointing down, here's our x, that's great, and then we'd be interested, right, we're gonna, because this is all in x, we're gonna have to make a change in variables for this to be completely sort of homogeneous. So if we look at a chunk of the load d c, then that's at a location c from the origin. All right, so we can start out by doing some forces in the y equals 0 to look at how the load and the shear are related. So just simply doing that, so we have v as a function of x minus v some distance down the line. And then, right, we've got a chunk of here, right? So we've got an integration plus x plus delta x, and then the load, wc dc. All right, and that's all equal to 0. How about we do this? How about we say 0 is equal to this, right? Because this is the same stuff. All right. So what we're going to do first off is we can look at this, and what we're going to use in here, we're going to make a mean value theorem statement. So the mean value theorem of integration allows us to say Wx at some average value times delta x is equal to that integration, right? So that's the mean value theorem of integration tells you that in some definite integral there is some average quote unquote value of the function Wx that you can multiply by the integration interval and get the same value of that integration. So we can write it that way. And then we have this piece over here which we can rewrite as Vx plus delta x minus v of x. Right, and that shouldn't be a plus. That should be, whoa, shouldn't be a plus. This is pointing downward. Oop, Control Z. That's interesting. Delete. That should be a minus. Right, and so this is negative right here. Whoa. Okay, negative. So here we have v delta x plus x over vx minus this mean value theorem derived value. We can divide out a delta x, and this should start looking sort of vaguely familiar. Delta x equal to minus w x bar, average value of wx. Take a limit, delta x goes to 0, take another limit, delta x goes to 0. And what we end up with here, right, as limit of delta x goes to 0, this is the derivative, right? This is the definition of the derivative. Vx plus delta x minus v of x over delta x says dv over dx is equal to, and as a limit of delta x goes to 0, that means x just goes to the center point, and so the average, right, we're collapsing this delta x to 0, so the average of this delta x period is x, right, because it's only a single point, and so now we have minus w x. So here we go. So basically we've just done the free body diagram of a section of the piece of the beam, and we've what's fallen out is the derivative relationship that we noticed from the free body diagram, or rather from the shear and moment diagrams that we drew in the last lecture piece. All right, let's look at the moment, which is going to be fundamentally the same, but just we're going to approach it in exactly the same way, but the sort of process that we're going to approach it in exactly the same way. We just have to do a couple more steps because it's the moment. All right. So again, we're going to sum the moment at the cut. Mx equals 0. Great. So let's go down here. So we have mx plus delta x, right? That's a positive moment minus m times x. Already we're getting set up here a little bit. Then we have, right, we're taking this cut here, right? So we're starting x to dx, right? So we have v x, and this is a negative moment. So minus vx plus delta x times delta x. Excuse me. So, minus x, or rather minus v del x plus delta x, minus v at x plus delta x times delta x, right? So, sorry, we're taking the moment about the x cut face, and we're a delta x away here. All right. Whew. So this, check. And then, of course, the load, right? So this is equal to each piece. And so we have, and this is again, another negative moment. So we have minus integral x plus delta x times the moment of each piece, right? So this is c minus x wx, or wc, sorry, dc. All right, so c is just a Greek letter, and I just butchered by drawing a little squiggle. All right, and this is all equal to 0. Great. So here we can do another mean value theorem and say x bar minus x w x bar delta x. So that's that piece, and then here we're going to rearrange this again. So we've got this. So we're going to rearrange these pieces. We're going to pull this over. And basically, actually, what we're really going to do is we're just going to pull these over to the other side, because this is already set up in that form we want to see, the m x plus delta x minus m sub x, right? So this is already the top numerator of that limit definition of the derivative. And so we write m x plus delta x minus m of x is equal to v x plus delta x plus x bar minus x w x bar times delta x. All right, so we can divide a delta x out by both sides, and we end up with m x plus delta x minus m sub x, or minus mx all over delta x is equal to v x plus delta x plus x bar plus minus x w function of x bar. Okay, so we've got this thing here. Now we can take a limit, right? So if we take a limit as delta x goes to 0, and a limit of delta x goes to 0 of this side, the limit sends this to v of x, right? Because the delta x collapses. And then the limit sends this whole thing to 0, because this, right, limit as delta x goes to 0 becomes just delta x, or just w of x, right? Because delta x collapses to 0, and so the point that we're analyzing is just a point. And then similarly, x bar collapses to x, right? So the limit of x bar minus x goes to 0. And so here we're left finally with the relationship that we're interested in or wanting to get at. So this piece right here becomes the derivative dm as a function of x over dx, and then all we're left with is vx here is equal to vx. And that is the second derivative relationship. So again, all we've done is taken the free body diagram of a small chunk of this beam and derived two what amount to first order differential equations representing the relationship between the shear and the moment on all three, and then also for previously for the load and the shear.